Okay, this hour we'll talk about activation function, although we have talked about it before, but I think we can show you some very interesting figures, okay, by using this class note, okay? So, again, the first activation function we talk about is sigmoid and maybe ReLU. And as you can see that in logistic regression, okay, its function looks like this, right? Basically, you can view it as a interesting neural network. Okay, you have only one input, x1, and you have weight to calculate the hidden value right here. And if you apply sigmoid function on this hidden neuron to get your y, that is exactly the same as logistic regression. So basically, you can use a very simple neuron and use the logistic sigmoid function to simulate logistic regression. Okay, so that's the interesting things. Okay, and the second thing that I would like to show you is that the reason why we have different activation function is because I think the first thing is that the output value is a little bit different. And as you can see that originally, okay, for this one, the blue one, originally we have sigmoid function, right? But the range of the output of sigmoid function is between 0.0 to 1.0. For some application, it is very useful. But as you can see that the slope, okay, right here is quite flat, right? The slope right here is a little bit larger, and the slope of the activation function, it indeed has certain impact. For example, when we talk about gradient descent, right? We usually write it in this way. Usually we write it in this way. Right? That is because when we applied gradient descent, okay, here, right here, your activation function usually, okay, usually your activation function will be part of your loss function. So when we do partial differentiation in gradient descent, and if your slope right here is a little bit small, and that means this value will be small, and that means when you perform gradient descent, every time when you toward your optimized theta, optimized parameter, this value will be small. So that means your gradient descent, you may need to take a lot of steps to perform gradient descent. So sometimes we use hyperbolic tangent, which is this one. And as you can see that because its upper range is between 1.0 to minus 1.0, and the slope right here, okay, we have a larger slope right here. So that means in those functions, when you perform partial differentiation, this value sometimes this value will be larger, and it helps you to have a better performance of gradient descent and so on and so forth. Okay, that is one of the reason. Okay, so in modern networks, most of the time we use hyperbolic tangent rather than simply just use sigmoid. That is the reason why. Okay, you simply just take a look at this, and sometimes ReLU is quite useful. That is because of the negative value of your input will become 0, and of the positive value from 0 to positive infinity, that will be still the same. So from the perspective of a neuron, that means if there's a neuron right here, all the information from the past, all the information received from the previous layer will be collected by this neuron, and they will try to process. There will be a lot of different weights right here. Those weights will decide, and the input value will decide whether this neuron will be activated or not. If it is larger than 0, that means all of the information will be passed to the next layer. If those weight and this output value are, for example, negative, the sum of them will be, is negative. That means this information is not important to this neuron, and those information should not be passed to the next neuron, to the next layer. So that is some explanation of ReLU. Okay, and since ReLU at this point is not differentiable, so sometimes we have different alternatives to replace ReLU, but it is okay if you use ReLU because of the packages. They will deal with such kind of special case when they perform partial differentiation. So it really doesn't matter you use ReLU or use some other alternatives. Okay, they have they sometimes makes the shape become differentiable at 0. Okay, so I'd like to show you something about the activation function. Here we have a circle right here. Okay, and we have x1 and x2, and you can see that it is blue, red, yellow, green, and purple, right? So if we apply different activation function on these two-dimensional plane, so you can see that if you apply sigmoid on this plane, on this input plane, okay, so at the right hand side, right here, that is x1 prime, which is the sigmoid of x, that's x2 prime, that's the sigmoid of x2, and you can see that for data point right here, it is original 0 and 0, right? But take a look at sigmoid. If the if the input is 0, the output is 0.5, right? So if you apply sigmoid on this surface, 0.0 will be pushed to 0.5 and 0.5, right? And all the data right here in this area, because all the data points right here in this area, their x1 is negative and x2 is negative 2, so the output will be 0, 0. So all the data point right here will be compressed to this single point, which is 0, 0. And all the data right here in this area, in this purple area, their x2 value is negative, so the output will be 0, but they will keep the x1 value, so L data will be compressed, will be pushed to this line. And again, all the data in this area will be pushed to this line. and all the rest of the data will be pushed to this line. So basically, a sigmoid is a nonlinear transformation. All the data point in this area, in the original area, will be, we say, compressed or be pushed to a smaller area. Okay, so maybe we can simply just clean this. Okay, as you can see that the purple one is right here. The purple one is right here, right? The purple circle is right here. Originally, it should be some data point right here, right? And all the green, for example, the green circle original in this circle, it will be pushed to somewhere near here. And such kind of compression is nonlinear. Okay? So again, let's take a look at hyperbolic tangent. Because the output value of hyperbolic tangent is between minus 1 to 1. So as you can see that all the positive data from the positive infinity will be pushed to 1. The other will be pushed to minus 1. And as you can see that the purple circle right here will be right here. Again, it is a nonlinear transformation from the original plane to this new plane. Okay, that's x1 prime, x2 prime. So, ReLU, again, all the negative value will become here. All the positive value will stay here. So that is how a different activation function to to move the data from the original space to a new space, to a new plane. Okay, if we have only two-dimensional data. Okay, so let's take a look at this figure. That is a very simple two-dimensional data, and it has two different categories: green, the blue ones, and the red ones. Okay. If you simply just apply ReLU on this x1 and x2, and you can see that all the data will be moved to the new plane, right? So if you simply just write a not that good boundary line between the red data points and the blue data points, and of course there's some misclassification right here, but if you take this boundary line and map it back to the original space, it may look like this. Right, as we mentioned before, because for ReLU, this data point, you can map it back to the original space, and that you can create the boundary line at the original plane. But as we mentioned before, there's still a lot of misclassification right here, right? So it is not a good way to simply just apply your activation function on your original data. And as we mentioned before, since we usually we first perform certain kind of projection on the original data, right? This kind of projection, this kind of weight will try to move, try to rotate, try to shrink or try to compress or try to modify this big X space, and then that would be a new space, as you mentioned before. And you can apply nonlinear transformation on that new space. Okay, so I'd like to show you some interesting examples right here. So that is okay. So we randomly generate this data. Okay, so the data looks like this. Okay, we have some data point with blue labels, and the other with red labels. Okay, so right here, I made this a very not a very complex, okay, a relatively complex neural network right here, but you can change it by yourself to see what is the difference if you use different structures. Okay, so input is 2, and we have 30 neurons right here with red loop, and we have 50 neurons with red loop, and we have 2 neurons with red loop, and we apply softmax at the end. Okay, you can change those neurons and different layers if you want to try. Okay, so that is the last layer. That means originally we have 2 different neurons at the beginning right here. So that is the first layer, right? And in the middle, you can design whatever neural network you have. But at the end, I still use 2 neurons to represent the data. So that means in that case, okay, we have 2 dimensions at the first layer, right? And we map the data to 30 to 50 different neurons, and then to 2 neurons. So that is a very large network, right? That's a very large network. So I'd like to show you how those data has been projected to the next layer, to the next layer, and to the last layer. Okay, so so here that is the neural network I'd like to show you. Okay, so as we mentioned before, you can always use get weight to obtain the weight value. So basically, you know how those weights and how to calculate all those weights and how to calculate the output value of each layer, right? So at the end, okay? That is the figure I'd like to show you. Okay, let's remove of them. Okay, I will draw it again for you. Okay. So that is the result of last layer. After the original data has been transformed to a very complex neural network, to 30 dimensions, to 50 dimensions, and go back to 2 dimensions. And I draw the data. Okay, so let's see that is, for example, x1 prime, that is x2 prime. And as you can see that I draw some circles right here, right? For example, that is the blue circles, okay, right here. And this blue circle will be transformed by my neural network to 30 dimension and to the 50 dimension and back to the 2 dimension, right? This blue line will be this one. And somewhere. And as you can see that it changes very how to say, strange, right? Because every time when we pass the data to our layers of neural network, and the information will be passed to the next layer, and that point, okay, that point will be mapped to a new space. That is the last layer of the space. And as you can see that those weights will rotate, move, shift, compressed, and perform activation functions. So that will be compress your data in a non-linear way. So that is a very complex mapping from the previous layer to the next layer, and again to the next layer, again to the next layer. So after 3 layers, you can see that the circles right here will become very strange because we apply several different layers and several different neurons and several different activation functions to push or to compress or to stretch the circles in this way. And at the end of that's there, and we can see that all those red data points will be, so here it is. That means x1 prime equals x2 prime. So the data point will be on two sides of this line. Why this line? That is because we apply softmax at the end of our neural network. So what is softmax? The easiest way to apply softmax is that, okay, originally we have H1 and H2, and we would like to apply softmax. So this value will become H1 plus H1 divided by H1 plus H2. And this value will become H2, H1 plus H2. And H1 plus H2 will be 1.0. Well, that is one of the definition of softmax. Basically, it looks like some normalization, right? But another explanation is that take a look at H1 and H2. If we perform classification in these 2 different categories, okay, usually we will select the one which has larger value. So basically, we would like to know H1 is larger than H2 or smaller than H2. If H1 is larger, then that means it belongs to H1 class. If H2 is larger, it belongs to H2. So basically, take a look at this one. If we have a line here, this line is x1 equals x2, right? So at this side, that means x1 prime is larger than x2 prime. And in this side, that means x2 prime is larger than x1 prime. So x2 represent to blue cluster, and x1 represent to red cluster. So that is red, and this one is blue. So for neural network, okay, if we want to perform classification, the neural network you design becomes very interesting things that we are trying to design different layers, and for each layer they map the original data to another space. If I design a neural network 30 neurons, that means I would like to project my original data, which has only 2 dimensions, to a 30-dimension space. And the projection has some, it needs some weight to do such kind of projection. And after that, we perform an activation function, which is rule right here. So it performs some nonlinear transformation. So it will try to compress, push, or try to move the data in the space. So after that, we have another layer, dense layer, 50 neurons. So it is another kind of space transformation. And with 2 neurons is another transformation. And at the end, we have softmax. So basically, this figure, okay, from the perspective of neural network, it is a very easy data set to perform classification. Because you can imagine that with certain kind of space transformation, it is quite easy to move the red dots and blue dots into two different areas. And you can simply just use a very simple linear line to differentiate these two sets of data points. Right. Again, we have some interesting things you can test. Okay. TensorFlow Playground. Okay, and take a look at this. It is provided by Google. Okay. And it has certain different configuration you can use. We have different types of data. You can use different features, different neurons, different layers. You can add neurons, add layers. Okay, right here. So it will teach you how different neurons they receive the information from the left-hand side layer and how to pass them to a right-hand side layer. And if you view it as a space transformation from different layers and how these layers are performed. Okay, and how they perform classification. So it's worthy to do such kind of things, to play with it. Okay, try to play with it. Okay, that's it. The other thing is that so after that we can we can draw a boundary line at the last layer, and we can map this straight line back to the original space. So you need to use this boundary line and go back to the 50 dimension and 30 dimension and go back to the original 2 dimension. So this line will be this line. That will be the boundary line. So it is a very quite easy thing to do such kind of classification, because you can imagine that after a certain kind of space transformation, you can indeed depart these two different data points, right? So here we again, I would like to show you a animation. Unfortunately, it is written in traditional Chinese, but I think the animation is still very nice for you to understand how a neural network works. Okay, so here only one. Okay, maybe this one. Okay. The animation is a little bit fast. Okay, but I will try to explain it. Okay, so we have two different data sets. Okay, the blue one and the yellow one. they somehow looks not that easy to differentiate them. But I will show you in this case, okay, this author show you how to use a very simple neural network to depart them. Okay, they have a very simple neural network on the left top side. 2 neurons, 2 hidden layers, 2 hidden neurons in a hidden layer, and 1 single output. Okay, and they use ReLU as the activation function. So here it is. Okay, so the idea is how a 2-layer neural network to solve binary classification. We have so that is its start. Okay, so it's a very simple neural network. Okay, so the first part is we have 2 inputs, blue ones and yellow ones. So the first one, we apply the first matrix. So it somehow rotate and this original data point to the new space and add a bias, so it moves to the right place. And again, we need to apply the activation function, which is a ReLU. So take a look at this one. ReLU does only preserve the positive numbers, right? So again, they perform the next transformation by using the second weight to the 1 dimension, and then add the bias. And after that, we simply just to see there's a boundary line on only 1 dimension projection. Okay, so we can see that it's very easy to differentiate the blue data points and the yellow data points. So that is how a 2-layer neural network to do such kind of complex binary classification. And those kind of classification cannot be done by linear models like linear regression or something. Okay, I think that's a very interesting animation. Okay, so let's go back. So that's it. Okay, we stop right here. That is, I'd like to show you the activation function.